Okay, so let's now one sec. Let us go into the main discussion for today. So we saw a bit of this in the previous lecture. In fact, we discussed one of these terms at great length, so I will not be elaborating that once again. Inasmuch as we discussed and described the temporal phase function phi of t as a Taylor series, in the spirit that it is important, we know it exists, but we do not know it until we measure it. This is also true for I of t or the square root of I of t, all of them, or for S of omega for that matter. All these need to be measured. It's almost the same as the wave function of quantum mechanics. Yes, there is psi, you solve for it, solving the Schrodinger equation, but you do not know what it is till you either deduce it or maybe even measure some aspect of it, right. But then okay, we had quite some discussion about this phi naught term, which is what we had called earlier as the absolute phase or the initial phase. Yeah, we got this going. The first term was the derivative of phi of omega with respect to time. We call this the group delay, and the dispersion in that quantity, the first derivative of phi of omega, the dispersion, that is the variation of that quantity with respect to frequency, is what we call group delay dispersion or GDD. GDD is material property like the refractive index. We ought to get as comfortable with GDD as we are with refractive index. It's like it's related to the dispersion of the refractive index for that matter, right. It's such a material property, right. So we can straight away see what the units of GDD is going to be. What do you think will be the units of GDD? Okay, let us do this sequentially. Units of phi are what? Phi is radians divided by omega is radians per second, but we have two derivatives with respect to omega. So, this is square. So, this is going to be seconds, some seconds square per radian, right. Whereas this would be, what should be the units of group delay? Maybe that's semi trivial as a question. It should have the dimensions of time, right. So, units either seconds, or in this case we can say femtoseconds or so. So, a popular way of writing the GDD of materials would be to write them in femtosecond square per radian for ultra short pulses. So, the zeroth order phase phi 0, but well, maybe we should take a step back and ask what are the units of phi 0. Phi 0 is just quantity in radians. It is just a simple dimensional analysis itself bears out the fact that it should be the same whether expressed or thought about in terms of in its terms as the zeroth order term in the time or the frequency domains, and hence you need to measure it. Any measurement of it can be considered direct measurement in either domain, right. And we elaborated this a lot. saying, look, if we have very short pulses, the shorter the pulse, greater the visual impact or even the impact of the 0th order phase, because it then becomes like a knob that which I can use to designate various pulses, various types of pulses, right. So, the cosinusoidal pulse, okay, but this is an angle, right. So, maybe we should sketch it like that. If this is a 0 shift, so then we have the, let me try and sketch this more neatly. And if I consider now a pi shift, this is, the shift is 0, here the shift is pi over 2. If it is pi over 2, then the pulse itself, okay, the way it is sketched in this figure, it is kind of like that. With the envelope function being so. So, at the maximum of the envelope, the field has a 0 crossing. So, we can call this a cosine, this is a sinusoidal pulse. Here at, I leave it for you to sketch how it would look at pi, at three pi over 2 all the way going back to 2 pi. So, all these the shapes of electric field in between. So, here there is a shape of the pulse, here there is another shape of the pulse. So, here there is a third, I mean it is a sort of continuous deformation. Okay, I do not know whether I should even call it a deformation, a continuous variation of the field the shapes of the field amplitudes inside, right. So, phi 0, the value of phi 0, especially for these very few single or even few cycle pulses, right, become really, it becomes a knob which I can dial. If I can dial this knob, around, I can generate different field shapes. And I brought up the discussion on field sensitive phenomena versus intensity sensitivity or variation of physical phenomena. And that if I were to now envision a very fast electronics which have something to do more with the carrier oscillation of these waves rather than the envelope, then that very fast electronics would certainly have something to do with this phi 0 term. And since phi 0 is also related to the relative phase difference between the maximum of the carrier here or here and the nearest field maximum, okay. This could be one way to characterize or measure out phi naught, such as it is 0 here, whereas for a pulse that is pi o 2 shifted, its nearest maximum is shifted pi over 2 from the 0 in terms of phase value. For the pi shift, it is shifted over by a phase factor pi, okay, with respect to the maximum of the envelope, that is the nearest carrier maximum is shifted by a factor of pi. We will see this in some more detail later on. So, this essentially becomes an offset between the carrier and envelope. So, we can call it FCEO as well, carrier envelope offset frequency. Okay. I mean, it's a reinterpretation of the same thing, but it will play an important role later on when we think more carefully about few cycle pulses and start using them in some context. This is indeed going to become a major factor. Whereas, on the other hand, if you take this 4 cycle pulse, then it seems that it still plays a role. However, if with some either insight or experience, we can envision the fact that since there are so many cycles underneath the envelope, the change, okay, in the shape of the electric field in the case of these 4, which is still very few cycles for the pulse, is not as dramatic. The most dramatic effects essentially in terms of this visual physics which I am doing present themselves for pulses which are extremely short, which is both challenging to produce, but also fairly challenging to maintain in a lab and use on a relative scale as compared to a 4, 5 or maybe 10 cycle pulse versus a single or a 2 cycle pulse. Okay, so that is the whole point. Notice that the 4 cycle pulses look alike, whether phi naught is 0 or a pi, whereas look very similar, whereas in the case of a single cycle pulse, even a tiny tweak of phi naught is changing its appearance and a lot more very quickly.